Hello friends, you're welcome once again to another fascinating math video. In this math video, we'll be looking at an application of the derivatives to solving electrostatic problem. This problem was taken from Halliday and Resnick from Physics, Fundamentals of Physics, but we don't want to show work on physics, rather want to show the application of the derivative on this physical problem. Alright, so I would also like to inform you that I render an online private mathematics tutoring service. So if you're interested in such a service, be very free to get across to me via the email I provided, or you can get across to me by my Telegram. The link is provided above, or you can still message me through Messenger. Then we can have a detailed discussion on how the class should be organized. Alright, so we want to look at this. The solution to this particular problem is indeed an atomic problem. Over here it says of the charge Q initially on a tiny sphere, a portion lowercase q is to be transferred to a second nearby sphere. Both spheres can be treated as particles and are fixed with a certain separation. For what value of Q over uppercase Q will the electrostatic force between the two spheres be maximum? Then this is my addition. This was not in the problem. I added it with my own discretion. It's a find an expression for the maximum electrostatic force. All right. So what I want to do, I want to show the application of the derivative in solving this problem. Don't forget this group is strictly for mathematical issues. All right. So I will not be bringing a pure physical issues here, but however, if a physical issue require mathematical ideas, we shall display the mathematical concepts and emphasize them. So let us look at the solution of this particular problem right away. So solution. Now, it is very important to diagrammatize what is being talked about in the statement of the problem. Now, we are told that we are given two spheres, and these spheres can be treated as particles. So we can draw out the spheres for clarity's sake. So the first of the spheres, it can be this. It can be this. We can consider this as a sphere. So okay, let me make it neat. I'll remove this from here now. This is the first of the sphere. And the second, we can choose this color, but they are identical. All right. Now, we are told that they are separated by a certain separation. So we'll put in the separation. Let's call it this. Then the distance between them, we can call the distance r, right? So this is the distance. So this is first sphere, sphere 1. And this is the second sphere, sphere 2. All right, so this is the situation. Now we have to find the value of Q as lowercase q over uppercase Q, for which the electrostatic force will be maximum. How do we find that? We want to apply calculus in solving this problem. Now, coulombs from physics, the man called Coulombs, he discovered that the force between the two particles is directly proportional to the product of the charges. Let's say it's Q1 sub Q2, and inversely proportional to the square of the distance between them, that is r squared. All right. So this statement of proportionality implies we have F equals to K Q1 Q2 over r squared. All right. Now, where K is a constant of proportionality. Now, we are told in the problem, let's look at the problem once again, that of the charge Q. Now, the total charge in this sphere 1 you are seeing over here, that is, I mean this, all right? The total charge there, we're told that is Q. So I can come here and write Q as its total charge, all right? Now, a portion was taken from it. What is a portion? Say a portion, so lowercase q, is to be transferred to a second nearby sphere, all right? So if the portion lowercase q is taken from the total charge uppercase q, what will be left? We'll be left with uppercase q minus q, all right? That will be the net charge on this particular sphere. While on this, the net charge will be q. So we can come here and write that the net charge on the first sphere is now q minus lowercase q, all right? While for this case, the net charge for this is q. Now, from this law is called Coulomb's law, right? From this law, we can say that our F is equals to K. Now, Q1 can be this, all right? So we have this multiplied by Q2 can be this, all right, over R squared. So this is equal to writing K. Now, this expression, the result for it is Q minus lowercase q, all right? Multiplied by this one is just Q. Everything over R squared. Hope you can see that. Now, this is equals to writing on expansion, we have the result to be, or rather, we can write it as KQ brackets Q minus lowercase q over R squared. Can you see that? And therefore, our F is equal to writing now, factoring out uppercase Q, we have KQ over uppercase Q. They'll be left with 1 minus Q over, okay, all right? Okay, we'll be left with Q rather. We'll be left with Q. So sorry, Q over uppercase Q. Can you see that? No, this, excuse me, this over here can be written as K uppercase Q multiplied by lowercase q. Hope you can see that. So this is very, very correct. Everything over R squared. All right. Now, what we do here, we say let x be equal to q over uppercase q. All right. So in that case, we have our q to be equals to qx. From whence I can call this one, let me call it, I called this star, right? So let me call it star star. From whence we shall have our force to be equals to kq. Instead of lowercase q, I'll put uppercase q, then multiplied by x. The same thing applies here. Now we say let this be x, so I can put it as x, then over R squared. Can you see that? Now page is exhausted. Let me take more page so I can continue the work. All right. So we have this as a result. So what we shall do, we shall expand. On expansion, don't forget that this can be conceived as a function of x, or the total charge on the first sphere is uppercase q, and it's considered as constant. So the only variable here is a lowercase q, all right? The portion that was taken out from the first sphere, we don't know the amount. So that can be considered as a variable. And because a variable is considered as a changing quantity, and if it is a changing quantity, we can perform calculus on it. All right, anything that changes is possible to perform calculus on it. There's a possibility if certain conditions are satisfied. All right, so in that case, we have this, then therefore we can say our F is equals to q squared x multiplied by 1 minus x, they're all divided by R squared, all right? And this can be further written as kq squared x, all right, minus we have kq squared x squared, then over R squared over R squared. And this is seen as a function of x. Can you see that? So because it's a function of x, we want to differentiate this expression. On differentiating, we have df by dx, which is equals to df of x by dx is equals to, right, now on differentiating the first term, we are left with kq squared over R squared. Differentiating the second term, we have 2kq squared x over R squared. All right. Now performing the differentiation again, We shall have the second derivative as the 2f